Recorded. We're going to be speaking. So today we're going to be speaking about benzene and the substituents. It's very important, okay? It's very important to note that these are going to be items where you have done most of this at A level. At this point, I think A level material is one of the materials where you should be very comfortable with by now. If you're not comfortable with your A-level material, please do go and revise it, and because we're going to be using that as a stepping stone, as a starting material. Okay, so benzylic halogenation. So if you want to add the group on the methyl of the methyl benzene, then you're going to be using the theoretical mechanism. Very important to note that this mechanism, okay, is actually a lot faster than what you would normally need for methane or propane or something like that, because the radical here is going to be very, very fast, okay? And you just need a little bit of UV light or heat, okay? This is faster than normal for radical substitution because the radical is going to be more stable. Unlike the electrophilic aromatic substitution, you don't need iron bromide, okay? Unlike the electrophilic aromatic substitution, you do not need iron bromide, okay? So again, that is something important to keep in mind, because here you have two reactions, okay, where you can have either the reaction on the alkyl group or the reaction on the methyl group. And in both cases, okay, you are going to end up in a situation where you are going to have a halogenation, or normally use the bromine, okay? And it will attack on different sides. So let's say you have a root, a synthetic root, okay? Keep that in mind. Now, this is something that even at A level, I'm pretty sure that at A level, you would have been fine with this, but I'm just emphasizing it because this becomes very, very crucial, very, very important, and it is something where you should keep it in mind to make sure that you know what you're doing. The mechanism of benzylic halogenation, okay, it is propagation. There are two propagation steps, okay? In propagation, normally you start with a radical, you finish off with the same radical. So this is something that you have done in the past, and it happens only at the benzylic position, because the radical on the benzylic position is going to be a lot more stable. And since it's going to be a lot more stable, then that will be the only position where the reaction will take place. If you had to try and extract a proton from the benzene, this is not going to be stabilized, therefore it's not going to happen. Please do keep it in mind. If something is not stabilized with resonance forms, then it doesn't happen, okay? Then it doesn't happen. What you've learned in first year still holds on true for this year. Now, benzylic cations, they can happen, okay? But it needs electron pushers, okay? An electron pusher would be something where, for example, the alcohol is going to attack and is going to remove the sulfonate, okay? So here, what you have is a good leaving group, okay? You do need a very good, strong leaving group. And once this leaving group leaves, produces a cation on the carbon on the benzylic position, and this cation, okay, can then be stabilized onto the ether, okay, and this ether is going to stabilize through a positive charge on the oxygen, okay, and therefore it's more stable than the parent benzyl or benzylic cation. So the parent benzylic cation would be the unsubstituted one. Okay, the pair in the benzylic cation would be the unsubstituted one. And here, always, okay, always, and I beg you to do this, draw the resonance forms. I have had plenty of students who do not draw the resonance forms. It never works. If you don't draw the resonance forms, it doesn't work, okay? You might have an idea of what should be happening, but if you don't draw the resonance forms, then it doesn't work, okay? I'm saying this because it's very important. SN2 is accelerated because it's easier to lose the bromide because you have a transition state that is delocalized. So the charges, so we normally in SN2 we have a transition state. So this transition state normally is not stabilized through the ring, okay, because there's no ring. But for a benzylic position, you have a transition state that is stabilized onto the ring, and what this ends up meaning is that it's a situation where you can have the charge all over the ring, meaning that the transition state is more stable, meaning you require less energy to produce a transition state, meaning it's going to be faster. Remember, every time we speak about transition states, it's going to be this point up here. So if for any reason that is lowered, okay, here it's lowered through stabilization in the ring, then the reaction will be faster, okay? Then the reaction would be faster. So this is something that you have to keep in mind. Benzylic acidity resonance in benzylic anions. So let's say you have a strong base and it protonates methylbenzene. Okay? Now, this negative charge is going to be carried through the ring, which means that at the end of the day, you're going to be in a position where your structure, okay, where your anion is more stable than what you would normally observe, okay, than what you would normally observe in a normal alkane. Therefore, the pKa is around 10 to the 10 times stronger acid. Okay, remember, pKa for a normal, for example, methane is around 50, okay, which means that if you have a pKa of 41, that is 10 to the 9. But the range is approximately there. 10 to the 10 sounds a little bit nicer to me. I'm emphasizing this because it's something that you should, in theory, have a good idea about. I'm not saying that pKa's, you should always know them by heart, okay? Far from it, and see, the pKa's, you should have an idea of what they're gonna be, okay? But the pKa's on their own, they mean nothing, okay? You need to know why the pKa is lower, and the pKa is lower than that of benzene, for example, or that of methane or that of alkane because of the stabilization. This is comparable to an alkane. Okay, ethene is then around 45. Okay, but this is comparable to propene. Now, for me, propene, if I remember correctly, it's a little bit lower than, it's a little bit higher than that. Let me confirm that. Yes, propene should have been 44. Okay, so there's a mistake in the PowerPoint there. Alkynes, so if there was a triple bond here, that would have been around 44. Okay, and what you get is that you can use butyl lithium to extract that proton. Okay, butyl lithium is very, very useful material. It's also very combustible. Butyl lithium is this one here. Okay, if you ever use it, never leave it outside in a room in Malta because it will normally just catch on fire. Okay, it's that dangerous. This will normally just catch on fire. So try to avoid that situation by always putting it in a fridge. Most chemicals do need to be put in a fridge. Okay, you might not be too comfortable with the idea of putting chemicals in fridges, but normally most labs will actually have stores, okay, fridges just for the chemicals. Okay, and that is something that, in fact, it is normally, and I'm gonna say normally, highly useful because it will ensure that whenever you are doing your reactions, then you're gonna be in a position where you would have you would end up with fresh chemicals that have not decomposed yet. Remember, a lot of chemicals, you put them in fridges because they are not that stable outside of the fridge. Okay? So, Benzylic Oxidation-Reduction reactions. Now, this is something that you have done it at A level, but any alkyl group can be oxidized to COH. It's any alkyl group. I'm emphasizing that any alkyl group because a lot of students think this is only for methyl. Any alkyl group will give you, okay, any alkyl group will give you the carboxylic acid. So if you have two alkyl groups, then you will have two carboxylic acids. Okay? And you are breaking the carbon-carbon bond. You are breaking a carbon-carbon bond. So always keep this in mind because in these situations, and I would like to emphasize, in these situations, you normally have a situation where you can easily do this reaction and you can easily get some useful products out of them. We're going to do the mechanism for this one. Okay, no need to know the mechanism for this one. I don't believe so. You can selectively oxidize benzylic alcohol. Okay, so to oxidize benzylic alcohol, you would need to use slightly weaker oxidizing agents. Okay, to oxidize benzylic alcohol, you would need to use a slightly weaker oxidizing agent than usual. So MnO2 would work better. Okay, and in this case, what you would be doing, okay, in reality, is to oxidize the benzylic alcohol and use stabilization in the process. So this is something where the reaction would actually be a little bit stabilized through the ring. Benzylic hydrogenolysis, this is unique to benzylic groups. In fact, a protecting group. Now, protecting group is something.
Sorry.
Yes, Jeremy?
So magnesium dioxide only oxidizes secondary alcohols? Only oxidizes secondary, like...
Only oxidizes benzylic alcohols.
Oh, that are on the carbon cycle of the benzene. Okay.
Yes. Okay. In fact, it would not work if you were to try and use something like ethanol, not ethanol, because ethanol, 2-propanol, for example, okay, or propan-2-1. That would not work, but it will work for benzylic alcohols. Now, MnO2 is also an oxidizing agent, so if you were to heat it long enough, probably will be able to. But look at the temperature here, 25 degrees.
Okay.
Okay, even dichromate. Normally, we use it to oxidize alcohols, right? But dichromate will only oxidize the alcohol if you heat it up. We distill, and we say we distill for obvious reason. But the reality is that without the distillation, it would not have worked, which is something you might not be completely accustomed to. So this is something that you should keep in mind.
Okay.
Okay? Now, Benzenol, or as we know it, phenol. So nomenclature, you know the 4-methyl-phenol or 4-chloro-3-nitrophenol, okay, or 3-hydroxybenzoic acid. So what you can see here is that chloro, nitro, and methyl are lower priority than the alcohol group, but benzoic acid has a higher priority than the hydroxy group. Okay, so that is something that, again, keep in mind. These are things where you might not be too familiar with, okay, but they are also very, very important. So keep in mind what I'm saying here with respect to these structures, because they tend to become very important later on. I don't emphasize on naming, so fl-eżami ħeġajdilkom penġuli di. I don't truly like that when it comes to naming, but I do like it when students know what compound I'm referring to if I give you the name. Phenol ethers, alkoxybenzenes. So you have methoxybenzene, and this is the phenoxy group. So if you need to name it as a substituent, that is the phenoxy group. Okay, we're not gonna try and name these structures down here. You should be able to. Okay, but let's not try. One of them is 4-hydroxyphenyl 2-butanone, been given. The other one is capsaicin. Okay, it's the active ingredient in hot pepper. But something like this, we are using the hydroxyphenol as a substituent of the butanone. Why? Because the butanone is a higher priority group. Okay, the butanone is a higher priority group. Therefore, you can use that to your advantage, okay, to your knowledge. Priority groups, I'm not sure how much you're comfortable with it or with them, priority groups, but priority groups are normally something that you should have learned even at A level. So we try not to waste too much time on that. Acidity of phenol. Now, this is another one where whenever you are speaking about the acidity of phenol, okay, you should be, in theory, speaking about its base. So when you speak about acidity of phenol, don't speak about how easy it is for phenol to lose an H+. You can't calculate that. You don't know that. Rather, speak about the ease, okay, of how easy it is for the base, the conjugate base, the phenoxydiene, to gain a proton. Okay, so what you do, instead of speaking about phenol is a stronger acid than ethanol because it can lose the H plus more easily. That's not the case. The case is phenol is a stronger acid than ethanol because its conjugate base is stabilized through the ring, therefore reducing the chances of the conjugate base reacting with a proton and reverting back to being phenol. Okay, so here what you have is, take a look. You see, the charge is going to be stabilized through the ring. And this is normally the mesomeric effect, what you normally incorporate as the mesomeric effect. We're going to name it as a mesomeric effect here. We are just stabilizing it through resonance. We are just stabilizing it through resonance. Okay? And that is something that you have to keep in mind. Emphasizing that these are important because everything we've been doing about benzene thus far has been, okay, has been to try and stabilize the ring through resonance forms. Okay, everything we've done thus far has been to try and stabilize the rings through resonance forms. Okay, so every time you see a resonance structure, you should realize that this is going to be important for stabilization. Okay, if you're unsure about how it works, if you're unsure about how it would work, don't worry. You can, one, ask me, and secondly, you can, if you want to, okay, try to work it out and figure it out on your own, and then ask me to see if what you've done is correct. I kind of prefer the second option, because the second option, you are being a little bit more proactive. I don't mind that students ask me and ask me questions. It's not the asking that would annoy me at that point. It's that you didn't try. So whenever you ask me something, please try to figure it out for yourself. Tell me, not say, what is this? Tell me, say, I was, or Matt, I prefer. Matt, I was doing the resonance forms and inductive effect of phenol. Why is it acidic? Because I can't see it. Okay, so the wording, that's the wording, to be honest. But one infers that you would have looked at it. The other one infers that you had no idea what you're speaking about overall. Okay, and for me, that would be a difference. That would be something that I wouldn't be too happy about it. Now, if you have the nitro group, you increase the acidity by 10,000 times. In fact, if you were to actually have, instead of the nitro group, okay, you were to actually give and use something of the sort of 3 nitro, okay, 2, 3, 2, 4, 5 trinitro phenol, the pKa would be 0. It would be a very strong acid. Okay, pKa of 0 is on par with not HCl. HCl is still pKa bigger, but H2SO4. Okay, it would be nearly as strong as something like H2SO4. And that is normally huge. Okay, that is normally huge. Now, so let's see why nitro group is so better at stabilizing this negative charge. Once you get the negative charge next to the nitro group, this can then go on the nitrogen and onto the oxygen. And remember, oxygen is very happy having a negative charge. Oxygen is very happy having a negative charge. Yes, you will end up having 2 nitro groups next to each other with a negative charge on both of them, but it doesn't mind. It's happy doing it. Okay, nitro group is always plus and minus. Adding a secondary charge doesn't do much. Adding a secondary charge will still work. Okay, so it's a situation where don't worry too much about it. At the same time, it's something that you should know. And here you can see that if you have 2,4-dinitrophenol, pK is around 4. And if you have 2,4,6-nitrophenol, like picric acid, now picric acid you might or you could have used in first year. Not sure if you've used it or not, to be honest. But if you have used it, picric acid is an explosive. Okay, picric acid is an explosive when dry. So normally we store it in water. But if dry, it will explode. Okay, if dried, it will just make a mess. In fact, I remember one of the first practicals we've had, Claude had gone ballistics. No, it wasn't Claude, it was Professor Borch, because he came into the lab and he realized that we were using picric acid on the bench and leaving it on the bench, which is something we later learned you should never do with picric acid, because picric acid would eventually dry up and explode. We're not using a lot of picric acid. We thought we were safe, but as he later told us was, whatever you do in your first week for practicals, there's a good chance that you might do it later on when you are doing your thesis, for example, your dissertations. And that was dangerous. This was one of our first practicals though, so I think we were forgiven for doing it. Now, having said that, okay, you can have different groups, okay, and these groups will have different effects. Each nitro group is making the acid around 1,000 times stronger. So 3 nitro groups would be 1,000 times cubed. In fact, you went from pK 10 to pK of 0. If you have something like a methyl, it makes no difference whatsoever. Okay, 10.26, and the pK of phenol, it's almost around 10. It is approximation of 10, so we can't even say it has increased. Okay, I'm emphasizing there's no major difference there because the reality is that the pKa remains pretty much unchanged. Okay, now, how do you prepare phenols? So if you remember correctly back from the days where you were at A-level, okay, you would have noted that for phenols, there was no preparation using the electrophilic aromatic substitution. And the reason for this is one of the simplest, okay, for chemistry. You don't have a preparation for phenols using EAS because you can never have OH plus. OH minus, very common. OH plus, not so much. Okay? OH minus, very common. OH plus, not so much. So whenever you would have wanted to prepare phenol, you had to find alternative routes. Okay? Now, electrophilic aromatic substitution needs OH plus. So what you would need some kind of substitution reaction. But we have also been told multiple times that breaking the aromatic ring is not favorable. Okay? So you cannot really, in theory, okay, you cannot really produce a compound or a reaction three-body SN1 or SN2. But this is actually possible. It's difficult, but it's possible. So throughout this lesson and tomorrow's lesson, we're going to prepare some phenols. Okay? And there's a mechanism not covered in these PowerPoints, which is called the Benzyne mechanism. And we'll also discuss it and I'll discuss that using the whiteboard. So there are 4 mechanistic scenarios, okay? You have electron withdrawing groups are present. So you have nucleophilic aromatic addition elimination taking place. You can have no electron withdrawing groups, okay? You'll need harsh conditions to enforce elimination, and this produces benzene. Maybe here I missed it. You can have a good leaving group, like the diazonium salt, to produce the phenyl cation, or you can use palladium. Now, this reaction won the Nobel Prize in 2010. And if you now go to do any of this chemistry, pretty much most labs are going to be using this reaction. Okay? Most labs will be using this reaction. And to be honest, as an opinion, you would be crazy not to. Okay? It's an amazing reaction. It works really well. Therefore, you would be crazy not to. Okay? So, nucleophilic aromatic substitution. So, in order to have a nucleophilic aromatic substitution, you need to have good electron withdrawing groups. Now, we normally say that electron withdrawing groups for electrophilic aromatic substitution, okay? Remember, electrophilic aromatic electron withdrawing groups will slow the reaction down. But here, the electron withdrawing groups will actually make it faster, okay? Here, the electron withdrawing groups will actually make it faster. Why? Because you need to reduce the electron density and place the electron density away from the substitution area. Okay? So you would literally need, okay, you would simply need to create a situation where here is going to be positively charged. So you need electron withdrawing groups. So this would work better when that carbon is delta plus. Normally, okay, normally when it comes to benzene, this doesn't happen. It doesn't happen for a very simple reason that normally when it comes to these kind of compounds, okay, there's simply no scope of having a positive carbocation or a positive carbon because you have electron density. And the electron density is going to be all over the ring. And the electron density is going to be all over the ring. Now, why the ipso position? Because you do need the mesomeric effect. Okay? The ipso position because you do need the mesomeric effect. Okay? So without that, then you will start to have a problem. You can either add the phenol, so make ROH, or you can add an amine to make phenylamine. Both will work, okay? And both will work exceptionally well, okay? Both will work, and both will work exceptionally well. Okay, so keep it in mind and try to do the reactions. This is the mechanism. As I said, you need to be transferring the charge onto the nitro groups, okay? If you have a meta-nitro group, there is no proper stabilization, so you can't really do it. And always, always, always note that we are counting and every explanation we're using the mechanism. So if you need to explain something in your exam, you show the mechanism. Okay, make me happy. I'm the person who's gonna give you the marks. I love mechanisms, so make me happy. Okay, apart from that, the mechanisms are very important because you're telling me what you know, you're telling me what you do, and you're telling me why. And I think that is exceptionally powerful, okay? Telling your lecturer, I know why this is happening. A lot of students don't do that. Maybe because they don't know why, okay? But this explains why you can have nucleophile substitution if you have powerful electron withdrawing groups. So something like phenol will kill the reaction completely. If you have phenol, this reaction would not work. Okay? If you have phenol, this reaction would not work. If you have methyl, this reaction will not work. If you have benzene or substituents, this reaction will not work. If you start having chlorines only, maybe, but again, probably it will be a bit of a struggle. It will only start to work as soon as you go to groups like the nitro group. Okay? It will only start to work as soon as you have groups like the nitro group. So those are things that you have to keep in mind. Benzene. Now, benzene is pretty much this group. So the first thing you are doing is you are eliminating, okay, HCl if you have a chlorine to produce, okay, you are eliminating HCl to produce a triple bond. This triple bond is highly unstable, okay, which means that this triple bond will very easily react, and which means that this triple bond, its sole purpose will be to react. Okay, this triple bond will want to in fact react with anything, including a nucleophile, even though there are a lot of electrons, because now you have created a position where you can add something to. Okay, so the addition reaction at this point will be favorable. Okay, now what this means is that you have to use strong bases, so NaOH or KNH2, KNH2, okay, which is a very, very, very strong base. Okay, I hope I've emphasized the very, very, very quite a bit there. Okay, it means that it can actually remove HCl. Now, once the HCl is removed, remember you have a strong base which will react with the HCl, and then the ammonia can react. Okay, the ammonia can behave as a nucleophile. Same with the NaOH. You first form the benzyl, and then you can add the OH minus. And this is what happens. So here, these two, you might tell me, what's the difference? The difference is if you have a carbon-14 labeled atom, okay? If you have a carbon-14 labeled atom, you will see that you will have two different products, okay? So that is something that is very important because carbon labeling helps a lot in understanding mechanisms, okay? And this is what the benzene group is. Benzene, it is highly unstable, and because it's highly unstable, the benzene, you should always try to not make it, because once you make it, it will immediately react. Once you make it, it will immediately react. Okay, so this is something that you always have to keep in mind. Now you might tell me, why wouldn't I want a reactive substance? Okay, and the reason isn't that you wouldn't want a reactive substance. The reason is that it's not the best way to make it. For example, if you look at the conditions, 340 degrees Celsius, 150 atmospheres, I don't think we have the capabilities of doing this reaction in the labs in Malta, okay, at university. Abroad, 1.5 atmospheres, I haven't seen, but 10, 20 atmospheres we have had in my lab. But again, it's not the most common. You'd start risking and you start having the possibility of people getting injured, okay, which you wouldn't want to have. So the first step would be the elimination, okay? So first you have a very, very strong base. The base must be stronger, okay, than the acidity of the benzene ring, okay? So if the benzene ring is pK44, you need something which is stronger than that. And the NH2 minus can get it, can take it, and the NH2 minus will then produce a carbon ion. This carbon ion, okay, this carbon ion will then kick out X minus, the leaving group. So even here, it's better to have a good leaving group, okay? But it kicks out X minus to produce benzene. Once benzene is produced, okay, once benzene is produced, then you can do one of the things. You can react with NH2 minus to produce another anion. This anion can then deprotonate ammonia, okay, and you will get your product. As we can see, it can react on both sides of the benzene, from there or from here, but it will give the same product, okay? This will give the same product. You can also have, and this will be the last mechanism for today, you can also have a super leaving group, okay? And the super leaving group normally is nitrogen, the diazonium salt. Now, reminder from what you've done in first year, where you can create diazonium salts by reacting an amine with NO2 minus in the presence of an acid, okay? And you will produce this one. This only works for primary amines. It will not work for secondary or tertiary amines. And the reason for this is that for anything bigger, anything that is secondary or tertiary, you will not have enough hydrogens to lose to produce the linear structure Rn2 plus. Okay, I'm not going to go into the mechanism. If you have problems with this mechanism, one second. No, we've done this last week. Then review what we've done last week. Okay, it's in first year. So I did this with your second years. Then, of course, due to delta G equals delta H minus delta S, leaving us, so due to this reaction. And remember, everything goes back to thermodynamics, okay? Losing a small gas molecule, the entropy will be huge. Therefore, these reactions are normally going to be highly spontaneous. In fact, to try and minimize this reaction, we normally do try and cool the reaction down. As soon as you want the reaction to take place, you heat it up. Okay? Normally around minus 10 degrees, this reaction tends to be fine. This reaction tends to be fine around minus 10 degrees. Then you add something like water and you can produce the phenol because we're preparing phenols. So in general, this will be first produce the nitro, then reduce to the amine, diazonium salt, and alcohol. I think this is still a very good way how to prepare this. Personally, I believe that this is still a very, very good way how to prepare phenols. Okay, so from the three mechanisms we've done thus far, this would be my preferred choice. Of course, we're going to be speaking about palladium catalysis during our next lecture, but for now, this would be my preferred choice. Okay? Now, when I say for now, this is my preferred choice, doesn't mean the other options, I don't consider them, because the SN1 itself, the substitution, is viable. It might be only viable under limited circumstances, but it's still viable. But you have to pay attention that you need to know when and how to use it. Okay? So that is something where I always make a claim that you should always know where and how to use a material. Okay? But we'll leave that for our next lesson. Okay? Because we're going to speak about the palladium catalysis. We're not going to do the mechanisms of the palladium catalysis. You'll do that later on in other topics. Okay? But it's a situation where at the end of the day, it's something that I think is very, very useful. Okay? Palladium catalysis is the future of chemistry. Now, when I'm saying that, it's probably been the future for the last couple of decades, so it's the present. But palladium catalysis has helped us improve a lot, and it has helped us a lot to make big jumps forward in synthesis. Okay, so for today, we're gonna stop here. If you do have any queries, please do not hesitate to ask. Okay, otherwise I will see you all tomorrow. Tomorrow we'll try and finish phenols. I'll speak a little bit about, I'll upload the papers by tomorrow, and I'll speak a little bit about some tutorial sheet work that I would like to give you over the Easter break. Okay? Mark, smartifitu xejjatkom u intom tal-eżamijiet?
No.
No. From what I've been told, it's going to be mid-April, after the Easter. So don't expect anything. I was waiting because I just asked just to ensure that I'm not the only one who hasn't given the full marks. Don't worry. I mean, I think it's going to be a bit later because of the Easter break, because we should normally do it in 6 weeks. And I think it's going to be around 6.5 since your last exam. That's not a problem. I mean, shouldn't be a problem. Don't wait for the marks for now. That's why I was going to say. If anyone, and I'm saying this because I know that you had organic for the organic 1, or sorry, you had organic 2 in your first semester. If anyone did poorly, or you might know that you've done poorly, and that, speak to me, okay, to see how I can help you improve. I'm not telling you I will definitely help you improve. That I can't promise. But there are some things that some students would be doing wrong when studying organic chemistry. So that is something that is a 5-minute chat that I could help with. Other than that, okay, please do speak to me and I will try and give you some guidance on how to do it, on how to work, okay? But don't worry. If you don't do well, this one, all of you will have a chance of getting an A and a B. Okay? Doesn't mean that everyone will get an A and a B, but all of you should have the chance of getting an A and a B. And I find that very important to consider when you are a student. Okay? This will be completely up to you. You work, you'll get it. Okay? I will see you all tomorrow, and until then, farewell.